Testing, microphone, testing. Okay. Looks like I'm the only one here. Here we go. Okay, perfect.
Is it you?
Yes. Hi, Deborah.
Hi, how you doing, Ryan?
Yes, doing well.
Good. Do you think you got some of the kinks out of the electronics?
I may have. I'm going to try something different today. I'm going to try to play it through YouTube, and perhaps it will be able to share. I'll be able to share my screen.
Yeah. Well, we'll see. I'm not perturbed.
Okay.
By it, but I know it's, go ahead. I think Stuart is not coming tonight.
Right. Yeah. Sam had informed me.
Yeah.
Yeah, but we'll give it a shot. I'm going to go ahead and share my screen and see if we can get YouTube to play. So just going to make sure I'm connected here. There we go. Okay, so sharing that, and now we go over to, I have a lot of tabs open. There we go. Oh, not that one. This one. Here we go. Is it playing okay?
Yes.
All right, perfect. So that's great.
It's a little garbled, but I think it might be the way the film.
Oh, that's just his voice. Yeah, that's his voice.
Yeah. Okay. I'm turning off at least the noise from my phone. Okay. All right. I'm yours, except for fun, which is my life is astronomy and geology and walking the streets of Paris on Google Earth.
Oh, I like that. That's pretty close to me. I do astronomy, earth science, and I also roam around Google Earth in my spare time.
Yeah. Yeah. Where did
What happened?
okay.
Captain, the Admiral's ship has been destroyed. What is the status of the Bold Cube? It has sustained heavy damage to its tower hull. I am reading fluctuations in their power grid. Sweet.
Now my screen is black, but I have captions.
Okay. Can you see it now in miniature screen? I think your microphone is going in and out.
Where's my microphone? And I can hear the dialogue softly and read captions, except not now.
Okay, do you have a visual though?
I have a visual of the black YouTube screen
Mm-hmm.
and you, yeah, on a little screen. Yeah.
Okay, did you see like the explosion?
Can you
just
hear me
happened?
better now?
Yes, I can hear you better.
No,
I can, yeah.
okay. No, no, it's a black,
So nothing's playing?
it's a black screen. Oh, mini screen I can.
The mini screen what? I think now you're,
No, I can see and you. What? How about, I'll turn off my phone. So there's no competing electronics. How's that?
okay.
My watch is still on, but anyway, I don't know what to do about the microphone.
Okay. Can you see like this green explosion on the screen?
No. No, no, you know, your finger icon to the screen, line, then I see a little image. But the big, like you just passed through the red line of the film.
Yeah.
Then I can see things.
Okay. But anyway, what I'm gonna do is take a screenshot here, just so there's at least a visual on the PowerPoint that I have.
Yeah, okay.
Okay. So yeah, let's take a screenshot of this. I'm gonna put it into Paint, and then I'm gonna copy that image onto. I see. It's not letting me do it. Okay, I see what the problem is. The computer is forbidding
I
me
see something.
sharing the YouTube clip because it's rented. So let me go back here. First contact explosion. Anyway, okay, this is more or less.
What is your main focus for today?
Yeah, my focus for today was these explosions in space. Maybe you can see this GIF. Try to zoom in. So here, all that green debris exploding.
Yeah, yes.
Okay, so this was what was just playing on YouTube.
Okay. I
What
see that. Yeah.
Okay. What I wanted to talk about was this idea of combustion in space.
Yes.
So here's
Yeah,
the power.
that. Yes.
And so my question is, can you have combustion in space? And after doing research on this, I found that it's impossible. You don't have these grand fireball explosions because there's no oxygen to fuel this conflagration of material.
Yes. I was thinking that when I watched this. Yes.
So when you see in the movie the Enterprise and the other ships are firing, I guess, explosives into that giant cube, you're seeing ejections of material as a fireball. And the only way that could happen is if there's some ignition and burning taking place. But if you're in a vacuum, that can't happen.
Yes. But
you may wonder, or people may wonder, the sun looks like it's on fire. Is the sun doing something similar to combustion? Because especially from this image, it looks like a ball of flames. And we all know that on Earth, flames have some fuel source to burn from. And they also have oxygen in the air to give it that red glow. And so you wonder, like, okay, what's the sun doing to make it look like it's exploding constantly, giving off this fire? Well, it's really a nuclear reaction. The sun is basically a giant nuclear bomb that's going off constantly at many orders of magnitude more than what we have here on Earth. But here on Earth, the way we make nuclear bombs is through fission, is when we split a really massive atom like uranium, and we release energy by doing that. But in the sun, it's a little bit different. Instead of splitting really big atoms, the sun is fusing really tiny atoms, such as hydrogen. And if we look at this diagram here, the very center of the sun, the core, this is where radiation is occurring from fusion. So in that blue center, hydrogen atoms, which are single protons, are smashing head-on and releasing energy. What's really interesting is we've never been able to replicate such a process here on Earth. We have not mastered fusion. We've been able to do fission, which is the splitting. We have not been able to fuse atoms together like the sun does.
so, well, I just see, what is a cold fusion?
Cold fusion?
We've not succeeded reputably in cold fusion, but I thought that we were doing hot fusion. And I never actually looked into it, but I thought that's what a hydrogen bomb was, as opposed to a uranium plutonium bomb. But I don't. Huh.
Okay. Yeah. So cold fusion is hypothetical. We haven't been able to make that practical yet.
Yeah.
So a thermonuclear weapon is basically a really small amount of uranium or sometimes plutonium, and the chain reaction of splitting that atom and then the other atoms knocking into more uranium atoms makes this chain reaction that releases enormous amounts of energy. So, for instance, the bombs that were dropped on Hiroshima and Nagasaki, they had like a certain expenditure of nuclear fuel. So they had like this much of uranium that was potentially explosive. But really what happened was only a fraction of that uranium actually reacted and blew apart the shell.
Oh.
And I'm trying to read through this really quickly, why they're called hydrogen bombs. Until it's completed. Okay. So I think fusion is more of like a secondary reaction that happens after splitting the uranium. And you can only be achieved for an extraordinarily brief moment of time. But I think what I was talking about earlier, I should have clarified, is that what we have not been able to replicate is a controlled environment where two protons can smash into each other and release energy.
Yeah.
Because the pressure and temperature is so incredibly immense in the core of the sun. Temperatures are close to 30 million degrees Fahrenheit. And, you know, those kind of numbers are just really unreachable here on Earth.
Yeah.
And cold fusion, you mentioned earlier, would be being able to fuse atoms together at room temperature. Because, like for the sun, in order to have fusion occur and release energy, you need to have a tremendous amount of pressure and temperature concentrated into a single spot.
Yeah. So the core of the sun is where the fusion action takes place,
Yes.
and the rest is more a result. The other outer layers fusion.
Yeah. You can think of the light being radiated away
Yeah.
as like the resulting of that fusion, because a lot of the energy is released as light. And then the mass of the sun, the whole giant ball, is really like the fuel tank. That's where all the hydrogen is for it to be fused together in the core. And then you have the other part, which is helium, which is the other byproduct of that fusion. So two hydrogen atoms come together, and now we have helium. And that helium sticks around the body of the sun.
Yeah. Does it stick in the core, or does it, Mike, looking it up, because helium also has two neutrons, so it's not just a simple 1 + 1.
Right. Yeah. And so
Where did I see there?
yeah, I think like deep into the core of the sun, you have nucleons that are disassociated from the rest of the atom. I'm actually gonna look that up really quick.
It's like a 2-3 stage reaction. I think one of the protons gets split.
Right. Here, let me.
Right.
Proton chain. Yeah. Okay, so here's basically the schematic. So the red balls are protons and the gray balls are neutrons. And so two pairs of protons will come together and they release energy. I think this guy is an electron and this should be a neutrino. Let me make sure. Oh, positron, I'm sorry. So it's an electron with a positive charge. So a positron and a neutrino are released. And we end up with is
There has to
now
be somebody.
a proton neutron pair and a proton.
Yeah.
Yeah, and these little gammas, these are the photons. These are light particles.
That's the radiation.
Or gamma ray, yeah. More specific.
My particle physics friends use the word photon very loosely and basically as an aliquot of energy, not necessarily light.
Yeah, not necessarily visible light.
It confused me,
So,
but something along the electromagnetic spectrum.
right. So a photon could be anything from a radio wave to a gamma ray. These are the force carriers for the electromagnetic force. So you can have all these different kinds of radiation, all being carried by a photon.
Yeah.
So when you turn on your microwave oven to heat your food up, you're shooting photons at your dinner.
Yeah. Yes. Yeah. Okay, so I was going to get back to the idea of combustion.
Mhm.
Our definition of combustion involves oxygen, the formation.
Exactly.
So you get an oxide of whatever it is, right? But
Yes.
can't you get the same phenomenon with other elements then, that when they combine, they give off energy? And would you ever call that combustion?
It's a good question. I've never explored that. So let's find out. That's really interesting. Combustion with something else other than oxygen.
That's, it's like we assume that life requires oxygen
So yeah,
on Earth, but all you need is.
so there has to be some oxygen present.
Cerium. What's
Cerium is either this guy, so ammonia or ammonium ceric nitrate, cerium and nitrate, or this guy. So oxygen is still present in these.
so cerium is an element?
Yeah. Okay, so here, look, you can have fluorine and chlorine.
Yeah.
That's interesting. I did not know that. That's really cool.
Yeah. It's like oxygen is a terrestrial conceit.
Yeah. That's a good point.
Yeah.
The other point I wanted to get to in the movie was this idea of force fields. So
Yeah.
I'm going to We can
Yeah.
find it.
Yeah, Lily's looking out the window at the force field
Exactly. Yeah,
at Earth. Yeah,
exactly. That's exactly what I was going for. So
Yeah.
you, what I'm talking about. And so I read this article that references Michio Kaku, who is a theoretical
Oh.
physicist.
yeah,
Whoops. And his point was, if force fields were a thing, if we could utilize force fields, why wouldn't we use them to build infrastructure? And he went on to say, like, if an advanced civilization was able to use force fields, we would, drive cars over them. We would make all of our buildings out of them, and with such little material.
so how would you, so what is, in the Star Trek world, what is a force field?
So in Star Trek, a force field was anything that would serve as a barrier between any rigid objects and radiation. So it's the reason they can breathe behind a force field. They can, touch it. It's a physical barrier. And I guess it would also insulate heat. So like heat is not being ripped out of the spaceship. What's
Right.
interesting is that you can see through it. And if you can see
Yes.
through it, that means radiation is penetrating through it. So it's a little bit of an inconsistency.
Yeah. So what do you
Um,
think it's made of?
If I were to give my best guess, I would say it would be similar to like the magnetic force. So the force you feel when you push two opposing magnets together, you feel that field. And if you were to like take a hold
Yeah,
of it,
yeah.
some window, right? I can see through the field that's repelling the magnets, but I can't break through it with my hand. It's incredibly strong.
Yeah. Yeah.
So later in this article, they say it's unlikely that we'd be able to build a force field such as the one seen in the movie because of a few factors. So let's take gravity for an example. Gravity has an infinite range. No matter how far you are away from a massive particle, there will always be a force attracting you toward it. And if you were to amplify that, because gravity is incredibly weak, you would have a hard time using it locally. And so then you go into electromagnetism. It's like, okay, what if we want a stronger force? But still, electromagnetism has this infinite range. No matter how far you away, no matter how far you are from a charged particle, you will always feel a repulsion or an attraction. And that leaves two choices now. So we ruled out gravity, we ruled out electromagnetism. What about the strong and weak nuclear force?
Yeah.
Well, their influence is so tiny. It's on the scale of atoms. So the strong and weak nuclear force are what responsible for holding nucleons together in atoms. And if you wanted a force field that was like a few inches or a few feet thick, if you wanted to have that kind of range, it really wouldn't,
Yeah.
strong and weak wouldn't be your best bet.
You'd have to, yeah, or you'd have to concentrate it or amplify it in the Star Trek world.
Yeah, exactly.
So I'm not a math physics person, but I'm thinking that gravity and strong and weak forces must or something, or is before
Must what something?
as you get away from the source of gravity, is it to the fourth power?
Oh, yes, it's 1 over r squared.
Or of
so
the
to
distance or
second
something
power.
like that? Second
Yes.
power, okay,
So if you
yeah,
move twice as far away, your
You're 4
gravitational
times.
force will be 4 times as weak.
yeah. 3 to 9, yeah. What was I gonna? Okay, so what, being able to measure on Earth, now I'm going to use the word mass for like a mountain or ice, or and they say that they know something is there because the gravity locally is increased. I'm not, it's like they're doing a gravity scan over an area of the Earth, and they can say that
Yes.
there is a local phenomenon because there's an increase in the gravity at that site.
Yeah, that can happen. The gravitational pull isn't constant across the entire Earth's surface. And that's because below the crust, you have different densities of rock. So
Yeah.
if you were like standing over a thin part of the crust, gravity might be a little bit weaker than it would be standing over a thicker part of the crust. And I think there is a map of the Earth that shows whether it's more or less than the average. Here it is.
Yeah. So that's interesting. It's, what is it? And you don't know if it's correlating with something that's in the mantle that you can't, that it, like in South America, it looks like it's in the Andes, but it could be something deeper.
That's right. Yeah. It might, I
That
think you
is not
can
on the
make,
surface for us to see.
yeah. I think you can make a connection though to mountains having a stronger gravity there, because you look at like the Himalayas on the top left above India, that's like a really big red spike. And you look like toward the ocean, like by the Bermuda
Yes.
Triangle in the Caribbean, it's pretty low. So you would probably think that if it's relatively flat, or if there's water, the gravity is going to be biased toward the low end, or if anything, just in the middle. Whereas if you have really dense mountains, which are probably made of granite and iron, it'll be a lot denser there, and gravity will act a little strongly.
So you think it's or it's said to be related to the density
Yes.
of the topography, the right of North America.
Mhm. Yeah. So variation is both the latitude, because it's due to the Earth's rotation. If you're closer to the equator, gravity is going to be a little less than at the poles. And think about it this way. If you're on, if you're standing on the Earth and you're standing at the North Pole, you're not really spinning. If anything, you're just turning in place. You're kind of
Yes.
standing still. Whereas if you stood on the equator, you're rotating over 1,000 miles an hour. And then you factor in that centrifugal force, you're kind of being flung off the planet just a little bit.
Yes.
So when you stand on the equator, the Earth, as it's spinning, is trying to fling you off. And that will actually make you weigh a little less than if you were to stand on the poles.
I'm moving. Yeah. Yeah, I see. Yeah.
And so the final factor they have here, which is local topography and geology, states
Yeah.
that the density of rocks is what's going to make gravity weaker or stronger.
Yeah. Yeah. Okay. Yeah. I'll look this up to read it more in depth later.
Yeah,
Yeah.
I think it's pretty. So yeah, force fields. It would kind of be weird
Force field. Yes. Yes.
to why not just build the whole enterprise out of a force field?
True. Yeah.
You wouldn't have to worry about damage.
And whatever. Yeah. Can you move a wall? Can you move a force field?
Right.
Sure.
Yeah.
Right.
Okay. And then we ask, how closely can you approach light speed? And in the film, toward the end, whoever's flying the ship, it's not the captain, is accelerating. He's like, "Oh, we're almost at light speed. We're at 20,000 meters per second." And
Yeah.
he is increasing his speed, and it's going faster and faster. And he's like, "All right, we're approaching light speed." And then you watch the spaceship just like zip into the distance, as if he really like just broke the speed of light and then went on for who knows
Yes.
how long. And there's a
Yes.
problem with this. The problem is you can't go from rest and then slowly start moving faster and faster until you get to light speed and then break it. Because relativity says, look, either you don't have any mass and you move at the speed of light all the time, or you're not, or you're not moving at that speed. And so us, terrestrial beings, we're stuck at being pretty much at rest. The fastest we've ever gone is only a fraction the speed of light. Here's the issue with going faster than light. So um, when you travel at great speeds, an effect known as time dilation starts to happen. And that means time will tick more slowly for you as you're traveling at a really fast speed compared to somebody who's at rest. So, and this is an actual phenomenon that you can experience here on Earth, albeit very, very slight. You can take a trip on an airplane and fly from New York to LA, and you will find that you have aged a few nanoseconds less than people who stayed home.
That's why all those people in LA look so good.
Yeah. So it's continuous. This time slowing down gets more and more pronounced the faster you go. If you were to travel at, let's say, 99% the speed of light, you'd find that while people who are staying at rest experience decades, only a few years will pass for you.
Yeah.
And so that's the effect. Special relativity that says that time is going to slow down as you increase your speed. And so here's the thought experiment. You start from rest and time ticks normally, and then rating and time ticks normal. And let's say you were able to reach the speed of light. What would happen when you reach light speed? Time would tick so slowly that it would just stop altogether.
Lorenz, what's Lorenz?
Yeah, trying to find the timeline. Here it is.
The other thing is, do particles, well, do particles gain weight as they approach the speed of light? Isn't there something about
Kind of.
that?
Yeah, kind of. They don't like necessarily accrue matter. They don't get heavier in the sense that it's like being more massive.
Yeah, accruing
What
matter.
it's really saying
Yes.
is their rest. Yeah. Their rest mass is getting greater, which means their inertia is increasing. So the faster you go, the harder it is to accelerate you even more. And you can make that analogy with mass. Think about it. What is harder to push, a shopping cart or a cruise ship? The shopping cart is a lot easier to push because it has less inertia. It's less massive.
Yeah.
And the same effect happens when you accelerate. Yeah. It's not that you're gaining matter, it's you're gaining inertia, which is the tendency to resist acceleration.
Okay. Yeah. Changing the semantics changes the concept.
Right, exactly.
Yeah.
I'm going to try not to do a lot of algebra in this meeting today, but
thank you. Yeah.
The point I want to drive home is with this little graph.
Yes.
Where if you're at zero, if you're at zero, this is where most of us will spend our life, traveling at 0% the speed of light. We won't really experience that much time dilation. But when you get close to the speed of light, you experience a lot of time dilation. And this graph doesn't quite get to 1. I don't know if you can see this. There's a little space. It doesn't quite meet the vertical axis here.
Yes. Yes.
But you can imagine, like, what if it did?
Yes.
What if you were a photon and you were traveling at light speed? You'd probably reason that time stops altogether. And this is true. If you're a photon, you don't experience any time. Time doesn't pass for you. And it's a little bit of a bizarre consequence. And it took me, hours of just thinking to myself, like, what would it be like to be a particle of light and not experience any time? So you'd run into trouble there. You'd run into a lot of trouble because the people on the spaceship traveling at light speed and then going beyond it would have a lot of explaining to do to the people who weren't with them when they meet up again.
In stars. That light in its way is, well, constant. It doesn't have a timeline, right?
Yeah.
So
Yeah.
if you're accelerating, if you're a person accelerating, it's one thing, but if you are light, it's another.
Exactly. Yeah. Imagine if the light coming out of your lamp, the little photons that are hitting your eye, decided to push the brakes and decelerate to only about half the speed of light. How, what would be going on? It would be quite a weird encounter.
Still be in the dark, or or what? Yeah.
The light would be experiencing time, and then the whole universe would break. It's weird. So the conclusion of this is to say there's a fine line between things that travel at the speed of light and things that do not. And this line never gets crossed. You can't cross it. Things that travel at the speed of light will never go slower, and things that are slower than the speed of light will never travel at speed.
Yeah. So knowing relativity, such minimal physics as you can gather, none of the calculations of this. Sitting, strictly as a layman and voyeur to this, I always thought of the absolute speed of light as doesn't exist in essence. And we can only see what we see because of the speed of light. But what if you had a different sort of perception of things, different sensors in your eye or whatever it is, different. Why is there the speed of light and the limit of it? But I just thought it was a human conceit in its way.
Yeah. It's a fantastic question. Why light speed is not only the value it is, but why it's finite. Why is it just a single speed? What if it was just only 10 meters per second?
Yeah.
And there isn't really an answer to that. But it's a really phenomenal question. Why is light speed the speed it is? And even the greatest minds in science have to toss their hands up and say, well, that's how the universe was made. Why is gravity just
Yeah. Yeah.
the strength
Yeah.
it is?
Yeah.
And it's thought like if these values were just a little bit different, as if God had a dial and was just tweaking it just a little bit off what we have it now, we may not exist.
And well, what about other wavelengths, for example, on the electromagnetic spectrum? Do they all travel at the speed of light?
They do, yes.
So yeah. So yeah, let's tweak the speed a bit.
That would be a fun thing to do.
Yeah, and I'm sitting here like, I don't know if you know the old fairy tale of the emperor's new clothes. These are from fairy tales. The emperor gets a new tailor who's renowned in zillions of dollars, and then it turns out that indeed there's nothing. He's just holding up his hands to air, and he walks, when the suit is finally made, he walks down the streets of the town, and everybody's oohing and eyeing, and the little boy doesn't know what the rules are, as indeed he was. But so I'm like the little boy, I don't know enough to say it, to say what relativity is, or so I can ask all these questions that out of ignorance.
Well, I did much the same thing.
True
Learning
ignorance. Yeah.
Learning all of this in college and grad school.
Yeah.
I knew very little, and was blessed to have other people show me the way. Right.
Well, as I am, and thank you. Yeah.
Mhm.
Well, so we're not going to have any force fields in the near future.
I don't think so. But it would be interesting to see if fusion takes off one day. I did watch a YouTube video yesterday discussing the consequences of using fusion as a renewable energy source. And as with everything, there are pros and cons. For one, it's extremely dangerous to have such a crazy environment in which fusion can take place. And if something goes wrong, it's end of the world.
Can't wrap it in boron or something?
Oh yeah, I don't remember exactly, but there was some way they could mitigate risks.
Oh wow. Wow.
And so we might be able to do fusion. I'm doubtful that we'll have force fields. I'm certain that we'll never go faster than the speed of light.
And then the conceit of this move to warp that the Borg can go through, and then the Enterprise follows it, and then they go back through the time warp, yet it's not a wormhole, right? So it's just a poetic license. Just the writers needed something, or what's with it?
Yeah, I think this was, what was this, 1996? Late in the 90s.
I forget. Yeah.
But yeah, it could be back then. Scientific understanding really wasn't that widespread. I think today it's gotten a lot better with our education and with the spread of technology, where if you go to anybody on the street and ask them, can you travel faster than light? I think majority of people will say, no, you can't. Everybody knows that. Whereas maybe 20 years ago, it may have been a different story.
No, the majority want. Yeah. Well, we covered a lot. Did you have anything else you wanted to bring up tangential to this, about that this movie broaches?
I don't think so. As I was watching the movie, I was just really trying to pick out the scientific aspects I could explore, and these three were the ones that stuck out to me. So I decided to go with them.
Yeah. No, they're great. Yeah. Oh. I had now I don't know if it was this movie or I started watching Ad Astra.
Okay.
There's a lot of guns involved in these. Do that. I mean, you wouldn't even shoot a gun on a plane,
Oh yeah. It's crazy.
Yeah, I can see whatever the ray thing is. I'm forgetting the term. But not a ballistic gun. But that's next week anyway.
Yeah.
Yeah. Huh. I know that there is a book called The Physics of Star Trek. Might be worth finding somewhere. I don't know who wrote it. I'm sure it's out there.
Yeah.
Yeah. Well, anything else?
No, I think this is a good place to wrap up. And I'm looking forward to doing Ad Astra next week.
Yes. Yeah.
So, yeah.
Well, thank you. I think you brought up, you picked some really great topics, and then, we went off in all directions, but it's good. Yeah.
Yeah.
Yeah. Cosmology. Yeah. Yeah. All right. Okay. Well, thank you very much.
Of course.
Yeah.
I'll see you on Wednesday.
I'll see you on Wednesday. Indeed.
All right.
Okay. Have a good one. Okay.
You too.
Bye.
Take care.
Thank you. Bye. Okay. That's out now.